Hi, we're going to talk about the linear programming farmer case made by myself, Ignacio Riera, and Isabella Daza. What is linear programming? Linear programming is a mathematical optimization technique. It is very useful when you want to maximize or minimize any specific objective function. It started in 1947 with George B. Danzig, who developed the simplex method. It can be applied in many different areas, such as efficient manufacturing, energy industry, transportation optimization, food and agriculture, engineering, etc. It is used to make processes more efficient and cost-effective. Assumptions. Severability. All values are continuous so they can take any real value. Non-negativity condition. All values must be greater than or equal to zero. Proportionality. The contribution of each variable is individual and proportional to its value. Additivity. The total contribution of the variables is the sum of the individual contributions of each of them. Certainty. All parameters of the model are known. Linear programming applied to farming. LP is very useful in farming, determining mathematically the optimum plan for the choice and combination of farm enterprises, so as to maximize income or minimize costs within the limits of available farm resources.
Okay, so our case for linear programming is going to be a farmer case. And it says, a farmer in Antioquia, Colombia has a small farm where he can grow coffee, beans, cocoa, plain, and avocado. The demand for the four types of crops exceeds the production capacity. Each crop requires, in different amounts, the following things: water, fertilizer, and land. The farmer sells 1 kilogram of coffee, cocoa, avocado for 1.5 euros, 2.5 euros, 1.8 euros, and 2 euros respectively. In the farm there are 4 million gallons of water available, 10,300 kilograms of fertilizer, and 8,000 square meters of land. The farmer wants to develop an optimal production policy in which he maximizes his profit. Here we have the requirements for each type of crop. For coffee, it needs 5,000 of gallons, 12 kilograms of fertilizer, and 2 meters square of land. Then for cocoa, we have 6,340 gallons of water, 0 fertilizer in kilograms, 7.5 square meters. For plain, we have 209 water gallons. We have 1 fertilizer in kilograms and 6 meters of land, 6 square meters of land. For avocado, we have 528 water gallons. We need 12 kilograms in fertilizer and 8 land in square meters. The values above represent the amount of water, fertilizer, and land necessary to produce 1 kilogram of coffee, cocoa, plantain, and avocado in the next 8 months. So here we have the capacity and profits of each type of crop. For coffee, we get a profit per kilogram sold about 1.5, for cocoa 2.5, for plantain 1.8, and avocado 2 euros. The requirement per kilogram for each crop is about water 4 million of capacity, fertilizer 10,300 kilograms, and for land we have about 8,000 square meters. And again, this capacity and profit refers to a period of 8 months. After getting all the data from each table, we got this, which is the objective function. So we want to maximize this function that I'm showing you right here. And where x1 is the number of kilograms of coffee produced, x2 is the number of kilograms of cocoa produced, x3 is the kilograms of plantain produced, X4 is the kilograms of avocado produced in the time.
This problem, we need to consider three constraints: water, fertilizer, and land. We need to create one inequality for each type of constraint. The coefficient for each variable depends on the amount of water, fertilizer, or land necessary to grow 1 kilogram of the product. In case number one, so water, for example, we put here 4 million because that's the 4 million gallons because that's the maximum amount of water we have. The same happens with fertilizer and land. We also have non-negativity constraints because it would make no sense to produce negative amounts of the 4 different types of crops. So then we set the problem up in Excel, which you can see in this slide. Using Solver, we get the solutions or the optimum values, which are the kilograms of each type of crop we need to produce during those 8 months to maximize our profits. These are the results. So, aiming to maximize profits, the farmer would have to produce the following amount of each type of crop. Coffee, 7,514.7833 kilograms. Cocoa, 0 kilograms. Plantain, 1,081.7388 kilograms. And avocado, 0 kilograms. These would result in 3,079.305 euros of profit. Now, the result of this maximization problem shows that in order to have the highest possible profit, which is 3,079.305 euros, the farmer should not grow cocoa or avocado. Instead, he should grow 7,514.7833 kilograms of coffee beans and 1,081.7388 kilograms of plantain. By doing so, he would have used all the available water and land, but will have 160.863 square meters of unused land. But what if during this period of time, instead of having the demand for all types of crops be greater than the supply, the demand for plantain was 900 kilograms? To maximize profit in this case, we would have to add another constraint for the demand of plantain, which is constraint number 4. The new results would be the following. The farmer would need to produce 680.8314 kilograms of coffee, 55.7762 kilograms of cocoa, 900 kilograms of plantain, and 102.5019 kilograms of avocado. These would result in 2,985.6916 euros in profit, which is lower from the original maximization problem we had, where the demand for all crops was higher than the supply, meaning that everything we produced was sold. That's it, and thank you.